a piece, I use filter paper because it works well with water as the solvent. I draw a pencil line a small distance from the bottom, okay? And on that pencil line, we can put tiny little samples of, well, for example, ink.
So you
Now,
can actually use like in nail polish and things like that.
yes, but then you need a different solvent.
Okay,
I'm using water as a solvent.
met die definisie het jy probeer sê substances. Is dit vertel ons substances?
It's substances. I'll explain to you in a moment. Okay. The chromatogram, you usually hang it up. You can put a ruler across the top of the container and a little bit of sellotape, and you hang your chromatogram up so that just the lower edge is in the water. We're using water as a solvent, so you can assume that the pigments that we are using are also water soluble. If I use, for example, a permanent Koki, I won't get a result because the permanent ink has a different solvent. But water as a solvent, many of your inks are water soluble. Those are probably all water soluble. Okay. So what is going to happen is the water is going to be drawn up this chromatogram. But together with the water, as it is drawn up the chromatogram, the pigment in the inks also dissolve in the water. And the water takes it up along the chromatogram. And we find very simply that if the water has reached the edge of the paper, then you stop the process, you take it out of the water. You will find that the different pigments will travel up to different heights. All right? If I had an extra one over here consisting of blue and green and red ink, then I will find the following over here. There, there, and there. Do you follow? Well, it depends on what pigments are used to make the black ink. Different companies use different pigments, okay, or different dyes. So you could do a chromatogram, and this is what they do in forensic science when they, for example, try and figure out which pen wrote the note. They can do a chromatography of the ink, and they can trace the ink. Well, if they've got the particular pen, they can trace it back to a particular pen. Okay. The larger companies with the fountain pens, the more expensive ones, have got specific batch lots that they know what dyes they use, and you can even trace it back to a specific batch lot on when you start investigating these things. Now, when we use colored substances, it's very easy to see. Oh, okay, these two had the same thing, those two contain the same thing, and those two contain the same thing. Can you see that? All right. Now, we can work out a mathematical volume. We talk about an RF value. Now, the RF value is the distance traveled by the substance. Okay, so distance traveled by substance. Okay, yes, divided by the distance traveled by the solvent. Distance traveled by substance, okay, divided by distance traveled by solvent. And then just remember, if I asked you which pigment is more soluble, the red one is more soluble. Why? It traveled up the highest. Okay. Along with the pigments. Now, for example, in medicine, they can test urine samples for sugars or proteins. These sugars and proteins do not have colors. So you're going to get a chromatogram with invisible spots on them. So what they go and do is they treat those invisible spots with something known as a locating agent. All right. Now specific substances require specific locating agents. But we aren't doing medical science now, so just very simply, this looks terrible, okay. A locating agent is just something they will spray on the chromatogram to allow the points to become visible. Do they have to have different colors? No, because if my chromatogram, if I have got one, there's my chromatogram, and there's my pencil line, and I had different spots of whatever substance I had on there, and I got a result like this. What can I deduce from my chromatogram? Well, let's say A, B, C, and D. It doesn't have to have a different color. It must make a visible spot because different substances have different solubilities. Okay. So we can go and figure out substance A and substance C shares one substance. Substance B shares one substance with A and one substance with D. Substance C contains something that none of the others have, and it corresponds with one point on A. All right. And then substance D has the same substance in it as B. Now they can use this for coloring in cool drinks to test which chemicals they've added. We can do it with sugars. We can do it with proteins. You can do a chromatogram with chlorophyll because the chlorophyll in the leaves of the plants, there are different types of chlorophyll. And you can separate out the chlorophyll types from a leaf by means of chromatography. The form in which we do it is very, very, very basic. You get specialized sheets containing like a silica gel, which absorbs the solvent better, and then when it leaves the spot behind in the gel, you can scratch the gel off and you can wash the pigment out to get it separate. Okay? Genes. The diagram that they show with the little lines on them that represent genes. Have you seen this in the movies? It's done with electrophoresis. They do a chromatography using a potential difference across a sheet. And the different proteins travel up to different lengths. And then they can identify the genes. They can separate them out by means of a very specialized form of chromatography. All right. So chromatography separates substances on grounds of solubilities. If you look in your textbooks, they're on page 30, where they say estimating purity. Which substances are pure, A, B, C, or D? Why? Only contains one thing. Well, okay, then it's not pure. But we're assuming now they're all soluble in the same thing, same medium. Okay. They say, page 10, just below point 2, you will notice that some dyes rise up the paper more easily than others. What is the reason for that? Some are more soluble than others. Those that are more soluble will rise up the furthest. No? Okay. Then they say you can test to see whether it's pure or not. In other words, if there's only one substance that separates out of it, you can assume it's pure. If there's more than one, it is impure. In the second paragraph, I'm just reading, they say chromatography that uses paper is called paper chromatography. There are many other kinds of chromatography. One useful kind uses a column of pure sand in a glass tube instead of the paper, and the liquid runs down instead of up. This is called column chromatography. Okay, and then if it's got sand, if you have substances left at certain levels within that column, you can remove it and you can wash it from that substance to separate the substance out. Okay. Yeah, not at all. You'll just do very basic paper chromatography and the use of locating agents. Yeah, but they won't ask detailed anything on that. No, they can ask you on paper chromatography, determine the RA value, and if the spots are invisible, what do you do to see them? You treat it with a locating agent. You don't need to know specific locating agents at all. It's just very basic. Okay. They say chromatography can also tell us about the purity of colorless substances. Two common ways of doing this. Use a locating agent. Okay. This is a substance that is sprayed onto the paper after the experiment and which reacts with the colorless spots. How do you know when the experiment is done if you have got colorless spots? When the solvent reaches the top of the chromatogram, okay. Okay, yeah. Because some people don't think of it. Okay, done. That's it there. Yes. Ja. Ja. I think initially it's trial and error, but I think at this point they know if the substance you are testing for is a protein, they will use a certain locating agent for proteins. If it's sugars, they will use one. There are very specific locating agents. That's why I say you don't need to know the names or codes or whatever they use to do that, but it is very specific. Okay. If you've got something and you don't know whether your substances are only water soluble, you will repeat the process with water, with a solvent that will dissolve ionic substance, one that will dissolve covalent substance, or one that will dissolve sugars or proteins or carbohydrates or whatever. Okay. No, you don't use petrol. Petrol is molecular. Mm-hmm. The problem with the petrol is petrol itself is a mixture. So you must use a pure substance as the solvent. Okay? You would have to use one specific fraction containing whatever. Do you understand? Okay. All right. That then on chromatography, right at the bottom of the page, there they refer to electrophoresis. An interesting kind of chromatography is electrophoresis. An electric potential difference is made on the paper by attaching the top and the bottom to a direct DC voltage source. This creates a potential gradient, and different molecules will be pulled at different rates along this gradient. And that is how they use it to separate DNA during DNA analysis. Okay. Next heading there, compounds and elements. Definition of a compound. Two or more substances, chemically bonded. In terms of an element, it's a pure substance consisting of one kind of atom. Both compounds and elements are pure. Okay? If I have a mixture, what is the definition? Two or more substance, not chemically bonded, no new properties, no energy uptake or give off. Yeah. Say again? Yes. Hydrochloric acid is actually a gas. And they dissolve it in water. Then you get, that's why you get hydrogen chloride and you get hydrochloric acid. When I work with a gas that's not dissolved in water, okay, then I have hydrogen chloride. The moment I go and dissolve that gas in water, then I have hydrochloric acid. Technically, no. It's very soluble in water, so if it goes into the air or into a medium where there is water available, it's going to dissolve in the water and then it will be acidic. There's moisture in your lungs. Yes, then it acts as an acid. Okay. They dissolve in the rain. They ionize. Acids are molecular. They aren't ions. But when they react with the water, they form hydrogen ions and the corresponding negative, the chloride or the sulfate or the carbonate ion. Okay.
So, kan jy vir ons weer daai papier gee van compounds, mixtures, elements, al daai definisie?
I will get it out. I will find one. Okay. All right. So then there in your books on page 12, they simply refer to the second paragraph. They have a look at chemical reactions. Now, in general, your books refer to chemical reactions as being non-reversible, but this is not entirely true. Many chemical reactions are reversible, so I don't like that choice. So when you refer to a chemical reaction, then you refer to energy that is taken up or given off, and what is done with this energy? What is the energy used for when I want a reaction to occur? That activation energy.
It is used for bonding. Honey, nutrients.
Before bonds can form? This is very important, people. Remember the graph with the activation energy. Okay? If I have hydrogen, whether it's exo or endothermic, and I get water over here, what happens over there? Yes, I require energy to break those bonds. So I end up with hydrogen atoms and oxygen atoms. Now they can collide with each other, and when bonds are made, energy is given off. So we use energy during bond breaking. Okay, and energy is given off in bond making. And the reaction is exo or endothermic depending on how much energy is used for bond breaking and how much energy is given off during bond making. If bond breaking requires more energy than bond making gives, then it's endothermic. If bond making gives off more energy than what is required by bond breaking, then it is an exothermic reaction. All right. Nee, ek wag nie vir Albert nie. Hy's fine. When certain hydrocarbons, we refer to them as fuels. Most of the fuels we use are hydrocarbons. Now, the definition of a fuel is a store of chemical potential energy. And in general, we find that the fuels require less energy for bond breaking than what they give out during bond making, so they are exothermic. And we use this heat then to drive cars, to generate electricity, etc., cook food, and so on. Okay. Now, they say we can, when a fuel burns, most of our fuels are hydrocarbon fuels. What does this mean? They are made up out of hydrogens and carbons. So when they burn, the bonds are broken between the hydrogens and the carbons. They react with oxygen, so the products for the combustion of a hydrocarbon fuel is always water and carbon dioxide. All right. They summarize a couple of bulleted points there on page 12. They say all matter is made up of chemical elements. The elements are often joined chemically to form compounds. Most of the matter around us is made up out of a mixture of different compounds. For example, air is a mixture consisting of nitrogen, oxygen, carbon dioxide, water vapor, a little bit of argon, helium, etc. Okay. Mixtures can be separated into pure substances. Remember, mixtures consist of elements and elements, elements and compounds, compounds and compounds. No? And they can be separated without having to break chemical bonds. So we say they can be separated by means of physical processes. Yes, that's like distillation or decanting or sorting. Yes, for a mixture. Okay. The next one, mixtures can be separated by physical techniques. We've just had that. And elements can be turned into compounds by chemical methods. When I turn an element into a compound, I'm going to make it react with something. So I'm going to break bonds and I'm going to make new bonds. So chemical reaction, then very simply making and breaking of chemical bonds. Then chemical changes, they have 3 bulleted points. A change in energy is involved. And then they've got the process is irreversible. Just put it in brackets. Sometimes it is, but it's not always. And the last one, the products are different from the substances that we started out with. They have new properties. So things like melting and boiling and evaporation and condensation are physical changes. We don't change the substance. But when we start cooking food or we start burning wood, then we get a chemical change, because we start out with one thing and we end up with something completely different. All right. Kinetic theory, all matter, one of 3 states, solids, liquids, or gases. The phase change from a solid to a liquid is melting. A liquid to a gas is evaporation. A solid to a gas, sublimation, and then it can go back, it can go from a gas, they can condense and form a liquid, and liquids can solidify and form solids. If a gas goes directly to a solid, we refer to it as sublimation. I see nowadays they put into the textbooks resublimation or deposition, just to distinguish between the 2 directions. No? Okay. Chapter 2. Let's just carry on with the stuff we've been doing. No, none of those tables are, you don't learn any of those things out of your head. Now, people, this whole first chapter is a little bit of, I don't think there's anything new except for the chromatography. It's just the differences between elements and compounds, pure and impure, mixtures and compounds or elements, etc. Now, in the next section, chapter 2, we are going to have a look at, well, basically, chemical bonding. Now, before we start off with bonding, I do the structure of the atom. What does an atom look like? Consists of a nucleus containing protons and neutrons. Okay, put one there. And electrons. Now, technically, I don't really need that ring there. Why not? It's just particles. There isn't a ring around the nucleus as such. There's not a ring keeping the particles together. What keeps these particles together? Just simple attractive forces between... What will a positive and a neutral particle do? It's electrostatic attraction. Because positives attract neutrals. If I didn't have any neutrals, what would these positives do? No, I did Coulomb forces and Van der Waals forces. If there were no neutrons in the nucleus, what will the positive particles do? They would repel. Would the nucleus be stable? No. So, yeah? Yes, but they do attract the electrons, but because the electrons don't form part of the central cluster. Oh, now I've got a wrong color over here. Let's do green. Okay, here are some neutrons. That is why the neutrons in the nucleus are there. It keeps the nucleus stable. What happens if a nucleus becomes too large? Like in uranium, when I shoot a neutron into it, they break up and we get nuclear reactions. But we are not busy with nuclear reactions now. So the chemical reactions that we work with do not involve the energy of the nucleus as such. It involves the energy with respect to the electrons. Now, electrons are negative, and you should know at this point that the negative electrons are found in shells around the nucleus. We have different shells. What's the difference between different shells?
The first one has 2 electrons and the rest is 8.
Yes, and what else? The first shell is the lowest energy. The second, so electrons with the least energy going to the first shell, next bit of energy going to the second shell, etc. Okay, now the electrons going into 28888 is not entirely true, but it's part of the model that we will work with, but there's a little extension on the higher level work where we go and have a look at the SPD distribution, but I'll explain that when we get there. For now, we are going to look at chemical bonds. So when one atom bonds chemically with another atom, the forces lie between the electrons, specifically on the outer shells. Chemical bonds involve outer shell electrons. And there are 2 basic ways in which we've done bonding. Which 2 bonds? Ionic bonding and Yes, we've done metallic and covalent bonding. And then we did metallic bonding, but metallic bonding is simple. It's just one metal ion with another metal ion and the delocalized electrons holding them together. All right. So, in general, when I burn a hydrocarbon fuel, I am breaking covalent bonds. All right. When I have an electrochemical cell, it's got to do with attractive forces between the ions that I can either break apart or put together. So, chemical reactions involve outer shell electrons, the bonds between outer shell electrons. Okay. How big are atoms and molecules? What's the answer to that one? They aren't big, they're very small. Okay. People, if I have 2 grams of hydrogen, just 2 grams, have you got an idea of how small 2 grams are? I will have 23. I will have so many hydrogen molecules. So 2 grams, I mean, that's tiny. It's tiny amounts. But look how many molecules of hydrogen will I have. Okay? So these particles are very, very small. They are so small, they almost don't exist. Okay? They say there on page 70, it's an interesting part there in the Did You Know, they say if you throw a bucket full of water, now a bucket is probably about 5 liters, a bucket full or between 5 and 10 liters of water into the Atlantic Ocean in Argentina, okay, and then traveled across the Atlantic Ocean to Namibia and take out a bucket full of the Atlantic Ocean there will probably be some of the molecules from your Argentinian bucket. It's because there are billions and billions and billions of particles of water in that bucket of water. All right. They say this is because there are many more molecules of water in a bucketful than there are bucketfuls of water in the South Atlantic Ocean. If I could count the particles in the bucket of water, there will be more particles than if I emptied out the whole Atlantic Ocean. I started filling it up with the buckets. The amounts of buckets used to fill the ocean will be less than the amount of particles inside a bucket. Okay, it's just ways to explain how very tiny these things are. Remember the structure of the atom? It's just a theory. We accept the theory because it explains what we want to explain. And this theory has been expanded, although at school level we don't go into the finer detail. But if you went and did nuclear science at varsity or wherever you went, then you will refine this theory. And that is why they work with the theory, because a theory can be adapted to explain certain phenomena as you discover them. Or they can throw out the theory and say, no, this theory does only explain up to here. We have a better theory, so we can throw out this one. Okay. Carry on with chapter 2. We started off, we said that atoms are extremely small. All right, that's the basics of it. Now, the atomic theory, we have the structure of the atom as we know it today, consisting of a nucleus made up out of protons and neutrons. And around the nucleus, we get electrons. Electrons are negative. The protons, we said, are positive. The neutrons are neutral. And I explained to you yesterday that the positives in the nucleus stay together because there are neutral particles in the nucleus. If there wasn't any neutral particles, the positives would repel and the nucleus would be unstable, it will fall apart. All right. The electrons are held in shells, depending on how much energy they have. Those with the least energy go into the first shell, then the second shell, then the third shell, etc. The electrons are also held by electrostatic forces. Remember, both the protons and the neutrons will have an attractive force on the electrons. When we did bonding in the previous years, we saw that electrons form pairs when they form bonds. The reason for this is, even if this was an electron, the electron is spinning around the nucleus. But as it is spinning around the nucleus, it is spinning on its own axis. The electrons that pair off have opposite spin. Because of the opposite spin, there is an attractive force between them. All right. And that is why they form two pairs. Okay. Now, this model, as we know it today, hasn't always been there. If we're going to have a look at the history, then there are 5 people who made, well, if one can call it discoveries. The theory started off with Dalton, and he just simply said, matter consists of tiny particles, which we still accept today. He said that atoms of different elements differ. In other words, a hydrogen atom looks different than what a copper atom would look like. And then he said that we can't make or destroy these atoms. And he said these atoms can join together. That's fine. Then the next one was Dalton. His theory is known as the billiard ball because it's just a solid particle. All right. Then J.J. Thomson was the next scientist. And he, well, said that there has to be another particle, the negative particles, the electrons, but initially they thought that the electrons were stuck inside this solid mass. Okay, and today we know the electrons are found around it. Now, Thomson's theory is also known as the current bun theory because his model of the atom looks like a piece of raisin bread, the raisins being the electrons stuck within the dough. the solid part. All right. Then came Rutherford. And Rutherford said, no, we have to have a central part, and these electrons can't be stuck in there. We find them outside of the nucleus. All right, so he said, we have a nucleus, and there's a space around it in which the electrons move. Then came Bohr. And Bohr refined Rutherford's theory further. He said, yes, these electrons we do find them outside of the nucleus, but we find them in specific energy levels. So the idea of the shells around the nucleus in which we find the electrons was then sort of brought into action. But there was still a problem, because as I've showed you, if the nucleus only consists of different positive particles, it's going to fall apart. And this is where Chadwick comes in. He said, in the nucleus, there is a second type of particle, a neutral particle, one that has no charge, that allows the positive particles to stick together, the neutron. And that is just very broadly, a very short summary of the development of the structure of the atom. This is there on page 20 in your textbooks. Now remember, I personally don't particularly like the history, but you are writing an external exam end of next year, and it is part of the syllabus. All right. So they've got it summarized very nicely there in a chart on page 20. You can have a look at that. All right. Now, when we go and have a look at the different particles, we find that a proton has a mass of, goodness me, 10 to the power minus 26. 10 to the power minus 26 of a kilogram. So it would be 10 to the power minus 23 of a gram. It's very, very tiny. That's a proton. Now a neutron has more or less the same mass. An electron is much lighter. If I remember correctly, an electron has a mass of 1,840th of that of a proton. Now you don't have to remember those values. It's just once again confirming the idea that these particles are very, very tiny. Okay. If we go to the periodic table, we find that the elements have a very specific arrangement. According to what rule are these elements ordered? Well, in the first place, according to the atomic number, because the atomic number is the number of protons, and this tells me which element we have. The atomic number, hydrogen is number 1, helium is number 2, because helium has 2 protons and hydrogen is 1 proton. Lithium is number 3, it's got 3 protons. Beryllium has 4 protons, so it's different from lithium. And so you can go on. Okay? So elements are arranged according to the number of protons. But why does the periodic table have the funny shape that it has? Why is there, 8 columns with a section in between? Well, yeah? Have a go? Yes, elements with similar properties are put together. All right, and that is how the structure of the periodic table was eventually developed or discovered, if you want to put it that way. All right, there's a very specific reason. It wasn't random. All right, so each element has a very specific place. The different groupings of the element is because they have similar properties. All right, and we will go into that a little bit later on. Now, protons, I've just said to you, have very tiny masses. Similarly, neutrons and electrons even less. So when we work with the atom, just to make things slightly easier, we tend to ignore the mass of an electron. So in other words, if an atom loses or gains an electron to form an ion, it doesn't affect the mass. All right. Because this is a very difficult number to work with when we start calculating, we say the mass of a proton is equal to the mass of a neutron, which has a mass of 1 atomic mass unit. An atomic mass unit. Just 1. And then eventually you will see, to make things even easier, we've taken it as 1 gram. Because if I pull out a proton from a neon nucleus, and I pull out a proton from a gold nucleus, will those protons be different? No. They are identical. All right, they are the building blocks. It's like houses. Houses are built with bricks. If I packed all the bricks next to each other, they will look the same. Or many houses, their bricks will be the same. But are the houses the same? No. All right. So, then on the periodic table, we say elements are arranged according to the number of protons. But we know, in the nucleus, what do we get? Protons and neutrons. So we get something that we refer to as the mass number. Now the mass number is the number of protons plus the number of neutrons. We can refer to them as nucleons. All right. The mass number is equal to the number of nucleons. So, if I have got 10 protons and 11 neutrons, what would my mass number be? 21. And in what unit would I write it? 21 atomic mass units. All right. When we write the symbol of an element, if the element is X, X stands for any element, then we find that the mass number, the atomic number is down on the bottom and the mass number is at the top. And you tend to forget that, but it's actually so easy. Waar is hy nou heen? There, okay? A to Z. First letter of the alphabet, last letter of the alphabet. A stands for mass, M-A-S-S. Z stands for the atomic number. All right. That one is the number of protons plus the number of neutrons. That one is the number of protons. So I can take any element, and I can go and, let's say I'll take sulfur. Sulfur is element number 16, and it has a mass number of 32. If I had sulfur 16 and let's say 34 over there, what does it mean? That's it, more neutrons in the nucleus. So what is going to be different? I have the same element, so the atomic number is the same because that determines which element we have. We've got sulfur. But what is different? It can sometimes be unstable, but it's not necessarily unstable. This 32 is equal to 16 plus what?
16.
Yes, but what is that? What is that 16? Yes, that is the number of neutrons. And this 34 consists of 16 protons plus 18 neutrons. What do we call atoms of the same element? Different numbers of neutrons? No? Not ions? It is something with an I. Ooh, you in grade 11, you've done them in grade 8, you've done them in grade 9, you've done them in grade 10. How about an isotope? Oh! Okay. These elements are isotopes of each other. Now she said at this stage, because the nucleus over here is going to be bigger, this one is probably unstable. Very often it does happen that some of the isotopes of elements are unstable, while the other isotopes are stable. You don't need to know out of your head which are stable and which aren't. Just you need to know an isotope is atoms of the same element, okay, but different mass numbers. Okay, and now, when we were at the course, and it's really stupid, they ask isotopes as a definition for 2 marks. All right? For this, you will get 1 mark. And I argued with him. Because I said if it's the same element, well, then it is the same number of protons. And if it's got different mass numbers, it implies the number of neutrons differ. All right? But to get the 2 marks, you have to say atoms of the same element, in other words, having the same number of protons, but they have different mass numbers, so the numbers of neutrons differ. It's like repeating the thing twice. But because it counts 2 marks, you need to have both. So just take note of it. It's really, really stupid. I argued with them with this one. And they said they're going to have a look at it. But please check if it counts 2 marks. Just explain the definition, because it's an easy definition. All right? Yeah. If it's 2 marks. If it's 1 mark, then the stuff written in green is fine. All right? It's not necessarily unstable if there are more. It's just because the nucleus becomes bigger, and then the particles maybe aren't as comfortable with each other. But sometimes it's the smaller nuclei that are unstable. Okay? It depends on from one element to another. It's usually the bigger one that becomes unstable. But there are exceptions, and you don't need to know which become unstable. Okay, so in your textbooks there on page 21, there's the heading Isotopes. And I want you to underline just below the table 2.4. They say, note that the 2 atoms, they've got chlorine there as an example, differ only in the number of neutrons. One atom has 18, the other 20. And then in the next line, atoms of the same element, which have different numbers of neutrons, are called isotopes. So just there by the same element, write in same atomic number or same number of protons. And different numbers of neutrons, they've got the different mass numbers, just that you have the whole double system going. All right. The next paragraph, they say 75% of the chlorine atoms are the first isotope and approximately 25% are the other isotope of chlorine. Now, when we get isotopes, for example, carbon has a very well-known carbon-12 and a very well-known carbon-14 isotope. These isotopes occur always in a fixed constant ratio. Hydrogen has 3 isotopes, hydrogen 1, hydrogen 2, and hydrogen 3. That has 1 and like that. And they occur in a specific fixed ratio. Now you don't need to know the ratios, just know that they occur in a fixed ratio. Because now the next thing that we're going to have a look at, if you're going to have a look at the periodic table, you will see that there are 2 numbers on the table. The one is the atomic number, and the other one is the mass number. But the mass number is very often a fraction. For example, selenium is 79.96. Where does that come from? Because the mass that they give is not the mass of a specific isotope. It is the average mass of all of the isotopes that you get in that element according to their ratio. Do you understand? And that is why we get half numbers or 127.6, 121.76. Very few of them in actual fact are whole numbers. But this is because they occur in a fixed ratio. And if I could scoop up a bucket of that element and I could work out the average mass, that is what they've got on there. All right. So don't let that confuse you. The periodic table that you work with in the exams, the one I always hand out to you, has got mostly whole numbers. I think it's only chlorine is like 35,5. It's just they've rounded it off to make it easier. All right. But if you go and look up on the internet and you get one of the more accurate tables, then you will see that it's not whole numbers. All right. Page 21, atomic and molecular mass. We've already worked with that. The atomic number, just very simply, number of protons. The mass is the mass of the average of the isotopes. And when we start doing chemical calculations, we will work with that mass as if it is in grams. So the value there is something known as a relative atomic mass. All right? Atomic mass, number of protons and neutrons. Why isn't it a whole number? It is the average. And then we go and work with it as if it is in grams, so it's relative. All right, the relative atomic mass. In your textbooks there, page 21, the second last paragraph, the middle of it, each isotope has a different nucleon number. That's the number of protons and the number of neutrons. And the relative atomic mass is the average of all the nucleon numbers of all the atoms in the sample of the element. Because of this, the relative atomic mass of most elements is not exactly a whole number. All right. Please mark off page 22, 2.2, B, D, and E, and 2.3, A, B, C. If you look at question 2.2, how many protons and neutrons? That's just simple using this method to determine it. But the next question is slightly more complicated. Have a look. They say, use the relative atomic masses given and calculate the relative molecular masses of the following compounds. Now the first one is ammonia, NH3. So the relative atomic mass of nitrogen, I will get it on the periodic table, is 14. And the relative atomic mass of hydrogen from the periodic table is 1. So what is the mass of this thing going to be? Yes, 14 plus 1 plus 1 plus 1, because there are 3. So we find that the mass of this thing using the relative atomic masses is going to be 17. So why don't we refer to it as its relative atomic mass? Why do they refer to it as the relative molecular mass? Yes, because I have a molecule. I do use the relative atomic masses, but in the end, this total is the relative molecular mass, MR. If I only had an atom, for example, calcium, would I say work out the molecular mass of calcium? No, I will say work out the relative atomic mass. Calcium has a mass of 40. So instead of referring to it as a molecular mass, because I have an atom, no, the relative atomic mass. They use another term if I have sodium chloride. Mass of sodium is 23 and mass of chlorine is 35.5. So what would this thing's total mass be? Yes, it's going to be 58.5. But now, do I have a molecule? Nope. Do I have an atom? Nope. I have a formula. Okay? So now, instead of referring to it as a molecular mass or a relative atomic mass, they tell you to work out the formula mass. They come from the relative atomic masses. Say again. For example, CO2. Like that. Oh, no, that doesn't matter. We work with it. We work with it. You work with it in its simplest ratio. When we do the chemical calculations, we'll come back to that question. Okay. Do you follow me at this point? I think I must stop here. Then you've got time to do the homework. All right? And that's it.
He should be everything. Strength provider, the architect of every ring. Experience penny, see the face of God in living.
I pray to God for my enemy. Why you baby, why not baby? Insta baby. Why you what your mama gave ya. Everybody move what your mama gave ya. Everybody shake what your mama gave ya. Everybody move, yeah, lost, fuck.
You are now watching the B10 Countdown.
This week on It's a Wrap.
I'm sure our government were also trying to do the best they could. I wish I could say that more convincingly, because I don't always really believe that, and nor do most of the people on the street these days. 4 or 5 years ago, maybe, but more recently, the money that was supposed to support businesses, individuals, people that are struggling for food, that was there. I know how much we paid over the last years in various forms of taxes and all the other businesses from my industry. So that for me was a bit of a disappointment. I think there should have been more support